Welcome viewers to the third segment of the eighth lecture for the online series of lectures for the course of linear algebra. Towards the end of the previous segment, we studied two examples of matrix representations of linear operators on finite dimensional vector spaces. We'll begin this segment with a question. So here is the question. What happens to representing matrix if two composable linear transformations are composed to yield another linear transformation. Okay. So it means that if T is a linear transformation from a finite dimensional vector space V to another finite dimensional vector space W, and U is a linear transformation from the finite dimensional vector space W to another finite dimensional vector space Z, then we know that we can compose these two linear transformations to find a linear transformation called U composed with T, which is going to be a linear transformation from the vector space V to the vector space Z, right? So now the thing is that if um, I choose um, a basis, suppose V is um, n dimensional, W is m dimensional, and Z is p dimensional. And to have these linear transformations to make sense, we want all three vector spaces to be defined over the same ground field F. Okay. Now we can form a basis B of the vector space W given by n vectors v1, v2 all the way up to vn. There are n vectors in this basis set since V is n-dimensional, so this is going to be basis, an ordered basis of the vector space, ordered basis of the vector space B, and then let us denote by B prime an ordered basis of the vector space W, and this is an m element set, and the vectors are denoted by W1, W2 all the way up to Wm. Okay, ordered basis of the vector space W. And finally, we denote by B double prime the set consisting of vectors Z1, Z2 all the way up to Zp, and this set is an ordered basis of the vector space Z, p-dimensional vector space Z. Okay, so now let us assume that A is the matrix representing this linear transformation T, relative to the basis b and b prime. So let me write it here. Let E be the representing matrix of the linear transformation T relative to the ordered basis calligraphic B and B prime. Okay. Also let B be the representing matrix of the linear transformation of U relative to the ordered basis B prime and B double prime. Okay. Now we'll establish the fact that we will establish the fact that B times A is the matrix representing the composed linear transformation U composed with T, this one, relative to the ordered basis calligraphic B and B double prime. Okay, so this is what we are going to show. Indeed, what we have studied in the last segment, with the help of that, we can write, given a vector v in the vector space V, we can write uh, the coordinate matrix of the vector TV uh, relative to the basis B prime is equal to A times the coordinate matrix of V relative to the basis B. Okay, this is because A is the representing matrix of the linear transformation T relative to the ordered basis B and B prime. This is why we can write this. Okay, now we see that the sky TV is in the vector space W. So, and since U is a linear transformation from um, W to the vector space Z, and TU is in W, so um, the vector u of TV is going to be in the vector space u of TV is going to be in the vector space Z. So we can write the coordinate matrix of this vector relative to the basis B double prime to be equal to um, B times the coordinate matrix of TV relative to the basis B prime. Okay, it is because B is the matrix representation of B is the matrix representation of the linear transformation U relative to the ordered basis B prime and B double prime. Calligraphic B, of course. Calligraphic B prime and B double prime. So we can write this. Okay. So combining these two equations, we see that U. So by the definition of composed linear transformation of two composable linear transformation is it's the same as ut of v vector. Okay, so that its coordinate matrix relative to the basis relative to the ordered basis b double prime is going to be equal to b times a times the coordinate matrix of the vector b relative to the ordered basis b. Okay, now it's immediate that u composed with t is a linear transformation. So from what we studied earlier in the 7th lecture, we know that we can always compose such two linear transformations to have a composed linear transformation u composed with t, which is going to be a linear transformation from the vector space v to the vector space z, right? And we always have a matrix, right? So this was what was the dimension of this guy? It's an n-dimensional vector space, and this is a p-dimensional vector space. So we have an p times n matrix over the field F, right? Representing this linear transformation u composed with t. Okay, and let us denote that unique matrix by C. Okay, so ut um, so for any vector v in the vector space v, ut v, if we consider this vector in this vector space z, and if you write the coordinate matrix of that vector relative to the basis b double prime, that is surely written as the matrix representing this linear transformation times the coordinate matrix of v relative to the ordered basis here, which is the ordered basis b, right? So we know that these matrix is a unique matrix. in the set of all P times n matrix over the field F. Okay, and from the uniqueness of that matrix representing this linear transformation U composed with T from the vector space V to Z, we know that C must be equal to this guy BA. Okay, good. So we summarize all these things formally by means of a theorem. Theorem 3, the statement of which is as follows: let V, W, and Z be finite dimensional vector spaces over the same field F. Let T from V to W be a linear transformation and U from W to Z be another linear transformation if calligraphic B prime, and calligraphic B double prime are ordered bases for the vector spaces V, W, and Z respectively, and if A is the matrix representing T relative to the pair B prime, calligraphic B prime, and B is the matrix representing the composed, and B is the matrix representing U relative to the pair B prime and calligraphic B prime and calligraphic B double prime, then the matrix representing the composed linear transformation U composed with T relative to the pair calligraphic B and B double prime is the product matrix C equal to B times A. Okay, so um, here this guy A is and and um, uh, A is going to be an so if I choose V to be okay, so I did not mention the dimensions of the vector space in this of the vector spaces in this theorem, but if I choose this guy V to be n dimensional and this guy W to be m dimensional and this guy Z to be p dimensional, okay, um, this is m dimensional, then this matrix A is going to be an um, m times n matrix over F, okay, and this guy B is going to be um, uh, P times M matrix over F. Okay, so this thing is going to be, so this is in F to the P cross M, and this is in F to the M cross N. So the whole thing is in F to the, this guy is in F to the P cross N, right? And it makes sense since U composed with T is the map from the vector space V to the vector space Z, right? Where V is n dimensional and Z is p dimensional. So the matrix representing U composed with T is supposed to be a matrix, is supposed to be indeed a matrix uh, of size p times n. Okay. Well, we should not write U composed with T belonging here, the matrix representation of this, right? Rather, a matrix representation of U composed with T should be in F to the P cross N, and which is indeed this product matrix C. So Theorem 3 states that fact. Okay, uh, now we should inquire what happens to this uh, representing a matrix when we change the ordered basis. Okay, in particular, we'll be interested in the change of the representing matrix of a linear operator on a vector space V under the change of ordered basis. Okay, so let me write it in words here. In particular, we will consider um, the situation when consider the case how oh, matrix representing a linear operator on a finite dimensional vector space change under change of basis, change of ordered basis. Okay, so let me put this question more specifically. Okay, let T be a linear operator, T be a linear operator on the finite dimensional vector space V over the field F. Okay, and also let calligraphic B to be the ordered basis denoted by this. So let us denote by B the ordered basis of the vector space V, which is the set U1, U2 all the way up to UN, and calligraphic B prime is the set U1 prime, U2 prime, all the way up to UN prime. Okay. Okay, so these two ordered bases of the vector space V. Now the question is, how are the mm, matrix representing T in ordered basis calligraphic B, okay, which we denote by by this according to our notation introduced in the previous segment, in the second segment. Okay, so how are the matrix representing T in ordered basis B? I should write, how is the matrix representing T in ordered basis B related to the matrix representing T in the ordered basis calligraphic B prime. Okay, and this is denoted by this T inside square bracket relative to the basis B prime. Okay, so how these two objects are related, that's the question more specifically. So before answering this question, let me digress a bit. It's important to note that if T and U are linear operators on a vector space V, and if this denotes this, and this denote the matrix representations of T and U respectively, relative to a single ordered basis B. Single ordered basis B. Okay, so both are expressed in the ordered basis B of the vector space V. Okay, so there are two distinct linear operators T and U on the vector space V, and there is a single ordered basis denoted by calligraphic B of the vector space V, finite dimensional vector space V to be more precise. Then by T inside the square bracket relative to B represents, so this is the matrix representing the linear operator T relative to the ordered basis B, and this is the matrix representing the linear operator U relative to the ordered basis B. Okay, so if this is the situation, then one can easily compose U with T to find another linear operator U composed with T on the vector space V. And by what we have studied so far, the matrix representation of this composed linear operator relative to the ordered basis B is just a product of uh, these two matrix representations. Okay, so on the left side is a matrix, right, and on the right side is a matrix. On the right side is a product of matrices. So an easy consequence of this fact is that the linear operator T is invertible. The linear operator T is invertible if and only if its representing matrix is an invertible matrix. If and only if its representing matrix is an invertible square matrix. Okay. This can be easily seen from the definition of an invertible linear transformation. If say we know that this linear operator T on the vector space V is invertible if U composed with T is equal to T composed with U is equal to the identity operator on the vector space, right? And this is equivalent to the fact that the matrix representation of U multiplied with the matrix representation of T is equal to the matrix representation of T composed, multiplied with the matrix representation of U. Everything is computed relative to the basis B. Okay, there is a single ordered basis of the vector space V. and this is supposed to be the identity matrix. So here I represent, I denote by I, the both, I denote by I both the identity operator on the vector space V and the identity matrix representing the identity operator on the vector space V. Okay, so both are denoted by the same symbol, I. Okay, uh, so this guy implies that this is equivalent to this thing. Okay, so so when this happens, we say that u is the inverse of the linear operator t on the vector space V. Okay, and then this immediately implies that T, the matrix representing the linear operator T inverse, you know, is is going to be represented by this matrix. So the matrix representation of this um, linear operator T inverse on V is equal to the inverse of the matrix representing the linear operator T relative to the ordered basis B. Okay, this follows from this because U is T inverse. Okay, so the product of these two matrices is the identity matrix, and then you take this guy on the other side, and then you have, you know, no, you keep it on this side and take this guy to the other side. So you have the the matrix representation of U relative to the ordered basis B to be equal to the inverse of this matrix. Okay. And you know U is equal to T inverse. So this holds. This is what we have written down here. Okay. So we numbered this equation by 13 in the lecture. So let me erase everything. I need room. Let me write down this equation. When t is invertible, then when t is an invertible linear operator on the vector space V, and B is an ordered basis of the vector space V, we can write this. This was equation number 13. Now let us get back to that question that we asked. Okay, remember the question? So we had a single linear operator, right, on the vector space V, and we have an ordered basis. We have two ordered bases of the vector space V. One is denoted by B and the other one is denoted by B prime. Okay, now we have a single linear operator on this vector space, and This is the matrix representation of the single linear operator T relative to the ordered basis B, and this is the linear, it is the matrix representing the linear operator T relative to the ordered basis B prime. Now the question is how they are related. These two matrices are related to each other. That's the question that we asked. Okay, so we have seen in Theorem 3 of Lecture 6, we've seen in Theorem 3, I want you to go back to Theorem 3 of Lecture 6, that there is a unique n times n invertible matrix P such that the coordinate matrix of any vector u relative to the basis B is equal to P times the coordinate matrix of the same vector u relative to the ordered basis B prime. And this is true for every vector u in the vector space V. This we have seen earlier. Okay, and we write this invertible matrix P in this way: P1, P2, all the way up to Pn, where P1 is the first column of the n times n matrix, P2 is the second column of the n times n matrix P, and so 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 on so forth. We have Pn to be the nth column of this invertible matrix P, so that Pj, so we can calculate the jth column of this invertible matrix P in the following way. Pj is going to be the coordinate matrix of the basis set uj prime. Okay, so remember what B prime was. B prime was this basis set u1 prime, u2 prime, all the way up to un prime. This was this ordered basis B prime, and the ordered basis B was u1, u2, all the way up to un. Okay, so how do you find the jth column of this invertible matrix P? We have seen in Theorem 3 of Lecture 6 that the jth column can be found by finding the coordinate matrix of the jth element of this ordered basis B prime, uj prime, relative to the basis B. Okay, so these are columns of the invertible matrix P. Okay, so now by equation number 8, so which was given in the second segment, um, we know that T acting on this vector u, so everything is happening in the vector space V. So the coordinate matrix of Tu relative to the basis B is equal to the matrix representation of this linear operator T relative to the ordered basis B times the coordinate matrix of U relative to the ordered basis B. Okay, this was equation number 8. So go back to the second segment and find equation number 8. We have seen it earlier. So now applying so we denote this equation by 14. Okay, this was 13 and this is 14. So now by means of equation 14, so now applying 14 to the vector Tu vector. Okay, that's a vector in the vector space V. One obtains, so replace U with Tu. Then we have the coordinate vector of Tu relative to the ordered basis B is equal to P times the coordinate matrix of the vector Tu relative to the ordered basis calligraphic B prime. Okay, so this is equation number 15. So we need this equation 14. We need this equation number 8 that was studied in the second segment, and we need this equation number 15. Okay, so let me create some room here to proceed. And then using these three equations, one has the coordinate matrix of this vector Tu relative to the ordered basis B is equal to P times the coordinate matrix of Tu relative to B prime, and this implies, so this using 8 can be written as the matrix representing this linear operator T relative to the ordered basis B times the coordinate matrix of U relative to the ordered basis B is equal to P times the coordinate matrix of Tu relative to the ordered basis B prime. And now this guy can be written down as the coordinate matrix, the matrix representation of the linear operator T relative to the ordered basis B times P times the coordinate matrix of U relative to the ordered basis B prime is equal to P times Tu, the coordinate matrix of Tu relative to the ordered basis B prime, and then I can bring this P here and then it will become P inverse, or you can multiply both sides by P inverse from the left, so that you have the identity matrix here and we have P inverse, the matrix representation of T relative to the ordered basis B times P the coordinate matrix of U relative to the ordered basis B prime is equal to, right? You can write this guy again as the matrix representation of the linear operator T relative to the ordered basis B prime times the coordinate matrix of the vector U relative to the ordered basis B prime, using this equation number 8 for the basis ordered basis B prime. Okay, and so which means that one has the following. One has this to be equal to this, right? Uh, the matrix representation of T relative to the basis ordered basis B prime is equal to P inverse the matrix representation of T relative to the ordered basis B times P. Okay. That's equation number 16. Okay, so I don't need these things anymore. I can get rid of them. So this is how, so let me write it here. This is how the matrix representations of the same linear operator T on the vector space V relative to the two ordered bases calligraphic B and calligraphic B prime are related. Okay, now let V be an n-dimensional vector space over F. B is equal to U1, U2 all the way up to UN, and calligraphic B prime is equal to U1 prime, U2 prime all the way up to UN prime, are two ordered bases of the vector space V. Now I'm going to use Theorem 1 of Lecture 7. Theorem 1 of Lecture 7. Okay. Remember so that had to do with two vector spaces, V and W. Okay. So let me recall the statement of that theorem. So there were two vector spaces in action, V and W. V was taken to be a finite dimensional vector space, and W is any vector space, and both defined over the same ground field F. And since V is a finite dimensional vector space, we choose the dimension of that these vector space to be n. So any basis, an ordered basis of this vector space consists of n vectors. We choose that ordered basis to be u1, u2 all the way up to un. Okay, then we choose any n vectors from this second vector space, which may be infinite dimensional. We don't know. So W1, W2, Wn, all the way up to Wn. Okay. So we had two vector spaces. V is a finite dimensional vector space. We have an ordered basis there given by these n vectors since V is n dimensional, and we choose n many vectors from the vector space W. And it's guaranteed that by the statement of theorem 1 of lecture 7 that there is a unique linear transformation T from the vector space V to the vector space W satisfying um, T uj is equal to Wj. Okay, so it's important to note that such a linear transformation is unique. So it exists and it is unique. So there are two parts of the proof. One is the existence proof and the other one is the uniqueness proof. We did it in lecture 7. So in the present context, we take both the vector space to be the same. So we choose V to be equal to W in the present setting. Okay, and we choose these set. So we choose these two vector spaces to be the same, and this is the basis B. So there is no change in notation in this context, and we choose this latter set to be the basis B prime. Okay, so we know that there is a unique linear transformation by means of this theorem. We know there is a unique linear transformation from V to itself, or a linear operator on V, linear operator U on V, such that U of this uj vector is equal to uj prime for j is equal to 1, 2, all the way up to n. Okay, so remember that here instead of wj we have uj prime. Okay, because we are choosing these n vectors to be the ordered basis b prime. So it's guaranteed that such a linear transformation exists and unique by theorem 1 of lecture 7. Okay. Now, we refer to, okay, so let me create some room here. Now we refer to equation 13 of lecture 6. Please go back to lecture 6, equation number 13, and excuse me, you will immediately see that where we discuss coordinate matrices. No, you know, we where we discuss how the for a given vector u of the vector space V, how the coordinate matrix of this arbitrary vector in relative to the basis is relative to the coordinate matrix of this same vector relative to another basis of the vector space. Okay, and there we see that the coordinate matrix, you know, we can write the 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 basis elements. There we see that. So let me go back to that equation of lecture 6. Equation 13. Okay. Yes. So yeah. So while deriving that, so it's actually basically the derivation of theorem 3. Okay. So there we see that um, so these are the basis elements of the ordered basis B prime of the vector space V. Okay. So we can always write these vectors as a linear combination of the vectors in the basis calligraphic B. Okay. And the coefficients of these linear combination are precisely the entries of that invertible matrix P. Right? We saw that in lecture 6. Okay, good. Where uh, J runs from 1 to n. This was equation number 13. And now let us get back to where we were. Uh, so we therefore see that um, using this equation, which we denote by equation number 17 in this case. So by equation number using equation number 17 and this equation together imply that u acting on this vector uj is equal to so I forgot this sum here. Okay, it has to be summed over all i's. Okay, I runs from 1 to n, and so we see from so together they imply that u acting on this vector uj is equal to sum of all these expressions pi j ui, where I runs from 1 to n. Okay, this is true for all j from 1 to n. This is our equation number 18. So now using equation 7, so remember what equation number 7 was. Let me write it for you. Equation number 7 was the matrix representation of a linear operator, right? TUJ uh, is equal to sum of all these expressions aij ui, where j runs from 1 to n. Okay, where A is the matrix representation of the linear operator T on the vector space V. So, using this equation number 7, we see that this matrix P is indeed the linear transformation, linear operator U. Using equation 7, one immediately finds that the matrix representation of the invertible linear operator U is relative to the ordered basis. Uh, yeah. Mm, So I'm writing this thing using the basis B. So relative to the ordered basis B is precisely this invertible matrix P. Okay. Okay, good. Let us try to summarize everything formally now, things that we have found so far. This is what we call Theorem 4. Let V be a finite dimensional vector space over the field F, and let calligraphic B, which is the set U1, U2 all the way up to UN, and calligraphic B prime is another set U1 prime, U2 prime all the way up to UN prime. These be two ordered bases for the vector space V. Okay, suppose T is a linear operator on V if P is equal to, if we write this invertible matrix, P1, P2 all the way up to Pn, where P1, P2, Pn up all the way up to Pn are the columns of these n times n matrix P. So this P is the n times n matrix with columns Pj is equal to the coordinate matrix of uj prime, the elements of this ordered basis, relative to the ordered basis B. Okay, then we have seen that the coordinate the matrix representation of the linear operator T, this linear operator T, relative to the ordered basis B prime is equal to P inverse the matrix times the matrix representation of the linear operator T relative to the ordered basis B times the matrix P. Okay. Alternatively, if this big U is the invertible linear operator on V defined by U acting on the basis elements of the ordered basis B is equal to the basis elements of the ordered basis B prime, where J runs from 1 to n. Then, okay, then the you know we have uh, we again have the relationship between the matrix representation of the linear operator T. you know we have the same relationship between the matrix representations of T relative to the ordered basis B prime and B, okay, the one that we have here. But now um, uh, these P's are nothing but matrix representations of this invertible linear operator U. So now this is not a vector anymore, this is a linear operator. Okay, so this is an alternative representation or alternative expression of the same thing. Okay, so here on the right hand side I have matrices, right? But but these matrices actually correspond to the linear operators U. Okay, these are matrix representation. These P is actually a matrix representation of this linear operator calligraphic U or PQ, whatever you want to say. Okay, where these the definition of this linear transformation is given here. Linear operator, sorry, linear operator is given here. Okay, so this was theorem 4. So let us take a break here. In the last segment of this 8th lecture, we are going to um, study two examples which will shed light the uh, on how matrix representations of uh, of uh, of linear transformations are affected by change of basis. Okay, thank you for attending this third segment of the eighth lecture.